In the previous section, we showed that accelerating charges produce electromagnetic waves. Like every periodic wave, they have a well-defined frequency and wavelength, where the product of the frequency and wavelength is equal to the speed of the wave. This is also true for electromagnetic waves, and when they travel in vacuum, they travel at the speed of light. Thus, the product of their frequency and wavelength is equal to c. The figure below is called the electromagnetic spectrum. It shows that electromagnetic waves exist with an enormous range of frequencies, from 10 to the 4th to 10 to the 24th hertz. Since all electromagnetic waves move at the speed of light in a vacuum, we can use the relationship above to calculate their correspondingly wide range of wavelengths. The boundary between adjacent regions is shown as a sharp line in the figure. The boundary is not so well defined in practice, and regions often overlap. Beginning on the left side of the figure, we have radio waves. Lower frequency radio waves are generally produced by electrical oscillator circuits, while the higher frequency radio waves, called microwaves, are usually generated using electron tubes called klystrons. Infrared radiation, sometimes loosely called heat waves, originates with the vibration and rotation of molecules within a material. Visible light is emitted by hot objects such as the sun, a burning log, or the filament of an incandescent light bulb when the temperature is high enough to excite the electrons within an atom. Ultraviolet frequencies can be produced from the discharge of an electric arc. X-rays are produced by the sudden deceleration of high-speed electrons. And finally, gamma rays are radiation from nuclear decay, which we will study in Chapter 31. Although all of the wavelengths in the spectrum are technically light, most people think of light as those frequencies that are visible to the human eye. From the figure, you can see that the frequencies of visible light make up a very small fraction of the total E&M spectrum. Your eyes and brain recognize light of different wavelengths as different colors. A wavelength of 750 nanometers in vacuum is approximately the longest wavelength of red light, whereas 380 nanometers in vacuum is approximately the shortest wavelength of violet light. Between these limits are found the other familiar colors that compose white light, as the figure shows. The association between color and wavelength in the visible part of the electromagnetic spectrum is well known. The wavelength also plays a central role in governing the behavior and use of electromagnetic waves in all regions of the spectrum.